Good morning, everybody. Today we are looking at our final set of notes for Unit 3, which means we're getting ready to begin Unit 4, and we have a test, which we will discuss later today in our Zoom class. And the final unit, Unit 4, will lead into our final. The final has been released by EKU. I will look over it sometime over the next couple of days and try to get a study guide together to give you guys an idea of what to expect when you take the final. So let's go ahead and jump into our notes today and finish up Unit 3. What we're doing today is we're looking at solving rational and polynomial inequalities. And it's not a challenging set of problems. It's just a matter of ensuring that you understand how to read the graphs, or how you whether or not you understand the algebra behind all the concepts that we're doing. So when we start with example 1, it says solve quantity x plus 3 times the quantity x minus 1 squared greater than 0 by graphing just that left side of the inequality. We can see because it's already factored, we can see that we have zeros at -3 and +1. And I will go ahead and I'm going to switch over and look at the graph itself on Desmos. I've already graphed this so that we can find other critical values and you can kind of see what the shape of the graph looks like. So here's the graph itself. There's -3, 0. There's 1, 0. We have a y-intercept at 0, 3, so we'll include that in our graph here in a second. But we just wanted to look at the general shape of the graph. So we'll go back over here to our notes. We have found that 0, or that y-intercept at 0, 3. So when we sketch this graph, well, you get the idea. That's what it's supposed to look like. It touches there at the x-axis at 1, 0. We want to find, what we're asked to do is find where is this graph greater than 0? Where does it lie above the x-axis? We can see from -3 all the way out to positive infinity, that graph lies above the x-axis. So that's the first step. The second step is we want to exclude any values where the function itself is equal to 0, because we're talking about strictly greater than. So at -3 and +1, we're going to exclude those values. So this shows us now that our interval is from -3 to 1, and then 1 on out to positive infinity. And so writing that out as a solution set in interval notation, it's -3 with the parenthesis because we don't include -3 to +1, and then from 1 to positive infinity. So if we write that out in interval notation, it's x such that -3 is less than x, less than 1, or 1 is less than x. And there's our interval notation. And this is the concept behind what we're going to be doing today. We're going to go ahead and look at example 2, where we're talking about doing this algebraically, and then we're going to compare example 2 to example 3, because the first method here in example 2 is algebraically. The method in example 3 is graphically, and hopefully you'll see the comparison between the two and how they relate based upon the techniques that we use. So for example 2, it says to solve it algebraically. So our first step is to subtract that x from the right hand side, and we generate this polynomial expression on the left where we have x to the 4th minus x is greater than 0. We can factor an x out of both terms, and then the quantity in the parentheses is the difference of two cubes, and so that's another one of those forms that we know how to factor. We get x minus 1, and then we have x squared plus x plus 1, and all this is greater than 0. So let's take our three factors and set each factor equal to 0 to find our critical values for x. The first one, x equals 0, it's already done for us. We don't have any work to do to figure out what x is equal to. The second one, we would just add 1 to both sides. And then on the third one, If you evaluate the discriminant of this polynomial, you'll find that the discriminant is negative, which means that this function only has complex solutions. So we don't have to worry about this one because it has no real solutions. You can also do the quadratic formula to verify that as well if you would like. So what this has done, if we picture this on a number line now and we plot these values, so here's our number line from negative infinity to infinity. We have an x value at 0. We have an x value at 1. This is effectively broken up our number line into 3 intervals, from negative infinity to 0, from 0 to 1, and then from 1 to infinity. And what we will do is take values within each one of those intervals and test them in the function x to the 4th minus x. And so in the first interval, I chose negative 1 as my x value. In the second interval, I chose 1/2. And in the third interval, I chose 2. So we just simply evaluate f of negative 1. And when we do that, we get positive 2. We evaluate f of 1/2, which is going to be negative 7/16. And then we evaluate f of 2, and we get positive 14. What we're interested in is not so much the values of these functions, but the signs at these test points that we've chosen. Are they positive or are they negative? So at negative 1, we see that the sign is positive. At 1/2, it's negative. And at 2, it's positive again. The function that we are solving for is where is it greater than 0. So if it's greater than 0, it has to be positive, and that's going to be on this interval and this interval. And since it's talking about strictly greater than, all of our solution sets will have parentheses. So the solution set is our first interval, which is negative infinity to 0, and our second solution set is from 1 to infinity. And if you want to do that in interval notation, or set notation rather, x such that x is less than 0 or x is greater than 1. And that's your solution set, and that's how you do it algebraically. Graphically, we're going to do the same thing. Essentially, we're going to be dividing the graph, though, up into intervals based on the vertical asymptotes of the function. And we can find those intervals, then we look at the graph and we determine where is it above or below the x-axis. And we're going to see that here in example 3. With example 3, it says solve the inequality by graphing x minus 1 over x squared minus 4. We can see from the denominator, x squared minus 4, that x cannot be negative 2, so we have a vertical asymptote at negative 2 or positive 2, because either one of those values would make this function 0, or the denominator 0, which would make the function undefined. We can also see from the numerator that it has a 0 at when x is equal to 1. So it has an x-intercept at x equals 1. We've looked at this graph before, so I'm just going to go ahead and sketch the graph out. This graph looks like this. And we've divided this up into our intervals now from negative infinity to negative 2. So this is just like the same process that we did algebraically, except now we're utilizing the graph as opposed to our algebra skills. And then our third interval is from 2 to infinity. Remember, we're looking at the x values here. The inequality is greater than or equal to, so we will include the values where the function is equal to 0, which would be that one x-intercept at 1. And we're only looking at where is this graph above the x-axis. Where is it positive? Because we're talking about greater than 0. So from negative 2, that's the, because from negative infinity to negative 2, the graph is completely below the x-axis. So it's always negative. Then we jump that asymptote, and now we have it's positive until we get to 1 on the x-axis, and then it falls below the x-axis and it goes to negative. So what that tells us then is that our first interval is from negative 2 to positive 1. We put a bracket around the 1 because we do include it because of the equality in the inequality. And then our second interval is from from positive 2 to infinity, because from that point on, the graph is completely above the x-axis for the remainder of its domain. And so there's the interval notation. As far as the set notation goes, we have x such that negative 2 is less than x, is less than or equal to 1, or x is greater than 2. And so there's our solution graphically. You can see that graphically the asymptote's divided up into the intervals, just like the critical values that we found in example 2 divided up into intervals for us to do the solution set. And then finally with example 4, we have this rational inequality that we want to solve algebraically. So it's very similar to what we did with example 2, but this one we have a couple more steps that we have to apply. Again, we start out with the first step being subtract this 3 from the right hand side to set up our inequality so that we can see whether it needs to be greater than or less than 0. So we have 3x squared plus 13x plus 9. I'm going to go ahead and expand that denominator for right now, which is just x squared plus 4x plus 4. And then we're subtracting 3 from that, and we're seeing that it's going to be less than or equal to 0. Now, in order to combine that rational expression minus 3, we have to get a common denominator. So we're going to take that negative 3, and we're going to find a way to write it over the common denominator to make this easy to work with. And the way we do that is we just simply multiply it by the denominator that we already have over itself. Because what I'm writing here in the pink, I think we can all agree is essentially the same as 1. So we're not changing the value of the negative 3, we're just writing it in a different form to make this function easier to work with. So when we start to combine things, we distribute the negative 3 through the numerator, and that gives us negative 3x squared minus 12x minus 12. And then we'll write that over our common denominator of x squared plus 4x plus 4. Still looking at this being less than or equal to 0. The 3x squareds will cancel. And what we're left with when we combine like terms in the numerator is x minus 3. And rather than write out that trinomial denominator, I'm going to go back to its factored form because that will make it easier to find critical values here in a second. And there's our reduced form of this polynomial or rational inequality that we began with. So we can see from the numerator, the 0 of this function, it would cross the x-axis at x equals 3. And then from the denominator, we can see that it is undefined, and that denominator is equal to 0 at x equals negative 2. So let's break this up into a number line again, just for visual representation. We have negative 2 and 3 are critical values. So that gives us these test intervals from negative infinity to negative 2, from negative 2 to 3, and then from 3 to infinity. So we want to pick values in each one of those intervals, and in this case we're talking about less than or equal to. So now we're looking at where is the sign negative or where is the function equal to 0. Those are our criteria for this one. So for this particular problem, I chose negative 3, 0, and 4 as my test points. So when I evaluate this at negative 3, I get negative 6. When I evaluate it at 0, I get negative 3/4. And then when I evaluate it at 4, I get 1/36. So the first one, the first interval, my sign is negative. The second one, my sign is negative. And the third one, my sign is positive. So we can eliminate this third interval because we're not interested in where is it positive. We're only interested in where is this negative or equal to 0. So our first interval solution is negative infinity to negative 2. Our second interval solution is from negative 2 to 3, but now we found that 3 is a 0, so that's where it's equal to 0, so we can include that in our values. And as far as the set notation goes, that would be x such that x is less than negative 2, or negative 2 is less than x is less than or equal to 3. And that's how you solve polynomial and rational inequalities. This is the last notes for Unit 3. We will begin our final unit tomorrow. Actually, I may postpone that and start it on Thursday. I don't know what day it is. Probably Thursday. Tomorrow's Wednesday. But we'll talk about that when we meet today during our Zoom class. So I hope everybody's doing well, and I do look forward to seeing everyone, that's all of you,